Hi everyone, and welcome to another video in this series going through some past exam questions on redox titrations. This is going to be the first of 4 videos where we do some iodine and thiosulfate redox titrations, which is one of the most common combinations of reactants that comes up. Similarly to what we saw in some of the questions with the manganate redox titrations, these questions tend to follow a bit of a similar pattern in that they give you an enormous amount of information to have to look through, and then they just give you an enormous blank space to write your answer in. So they kind of look similar, these questions. I'm not going to read through all of this. I'm just going to go straight to the question and see what it wants me to do. So the first thing it says, for steps 1, 2, and 4, write ionic equations including state symbols for these reactions. Okay. Then we need to determine the percentage by mass of copper in the brass. There's a lot to do here. So let's just focus on doing these ionic equations first. So we want to do an ionic equation for step 1, first of all. So what's going on in step 1? We had 2.8 grams of brass. It was reacted with concentrated nitric acid. And we had these two. Okay, so we've got 2 half equations. So all we need to do is combine these 2 half equations together to make one overall reaction. So the way we're going to do this, we can see this is our oxidation half equation. Copper's losing 2 electrons. And then in this half equation, it's a reduction because it's gaining electrons. But to get these two to combine together to make an overall reaction, we're going to have to times this second half equation by 2 so that the electrons would cancel out when we add them together. Okay, so I'm just going to go ahead and do this then. So we want the copper here. It does say including state symbols. Okay, so we need to put this on. And then I'm going to multiply this second half equation by 2. So I'm going to end up with 4HNO3. It's a bit unusual here to have the state symbol L for liquid. Usually these are all aqueous, but this is just liquid because it's saying it's concentrated nitric acid, so it hasn't been dissolved to make a solution. Right, and that's it. That's all that's on the left-hand side. With the electrons would cancel out, so that's it. It's just copper and nitric acid. And then what it's going to make is it's going to make the Cu2 plus ion. It's going to make all of this lot then multiplied by 2, because we multiplied this equation by 2, didn't we? So it's going to make 2NO3 minus. It's going to make 2NO2 gas, and it's going to make 2H2O. So that is our step 1. Let's just make that clear for the examiner. Okay, what about step 2? What's going on here? So it says excess aqueous sodium carbonate is added to neutralize any acid. The mixture effervesces and a precipitate forms. Okay, so what I'm going to do with this one is I'm just going to write a normal equation and then turn it into an ionic equation. And then I can cross out the first equation and just make it clear that this is the one that I want marked. So we're doing sodium carbonate. So sodium carbonate is Na2CO3. And again, we need to be doing state symbols all the way through. So it says aqueous sodium carbonate is added to neutralize any acid. Okay, so that's going to be reacting with the nitric acid here. The mixture effervescing. Okay, and that's it. Right. So if it's effervescing, it's effervescing because it's going to be an acid and a carbonate. So it's going to make carbon dioxide gas. And a precipitate forms. So this is interesting. So why are we making a precipitate here? This should just be making sodium nitrate and water and carbon dioxide. Okay, and so sodium nitrate's not going to be a precipitate. Okay, that's just going to be it's going to be soluble sodium nitrate. So why is this happening? What's going to happen here is the fact that we've still got we're adding it to this solution. So we're trying to think of, well, what's going to make a precipitate here? There's nothing here. This is, initially confusing. The only combination here is that we've added the sodium carbonate to this reaction. So yes, it's going to react with the acid, but could potentially react with any of the products of this reaction as well. Okay, because all of this stuff's still going to be around. And the only combination here that's going to end up making a precipitate is if it makes copper carbonate. That's going to be the precipitate. So that's going to end up changing this equation quite a bit. So we're going to make carbonate, we're going to make copper carbonate. That's going to be the solid. Carbonate we know is a 2 minus ion, right? So it would be copper 2 plus, so it would just be copper carbonate like this. So then what's going on here then is, actually we can write this as two separate things is probably the easiest thing, or we could write it all as one equation. It doesn't matter, I'm just looking at the mark scheme here. Yeah, they'll let you write it as two separate reactions or all in one go. It doesn't matter. Okay, so let's just do it all in one go, that'll be easier. So what we would make here is we'd have to have our plus copper ions on this side. Good job I said I was going to do this in a rough version and then sort it out, didn't we? So we'd have those there, and then we'd also end up making sodium nitrate, which would be, which would be aqueous, and water as well, wouldn't we? Right, and then just balancing this then, what's happened here, we'd have to have the carbonate, so one of the carbonates is going to go there, so we need two carbonates, one that's going there and one that's going into the carbon dioxide. So I've now got 4 sodium, so that's going to have to be a 4 there, and I've got 4 nitrates, so that's going to have to be a 4 there as well. Let's just check that works then. So 4 sodiums, 4 sodiums, 4 nitrates, 4 nitrates. The 2 carbonates end up as 1 there and CO2 plus that oxygen. The copper is a copper, and I've got 4 hydrogens here. So I'm going to have 2 H2O there. Okay. So then, does that work? 2 oxygens. Yeah. So, no, hang on. So I've got 4. Sorry, bear with me here. That's 1 carbonate, and then my second CO3 is going CO2. Yeah, this is why it's going to be awkward. Let's just write this in terms of balancing. This is going to be a bit of a nightmare. So let's write this as an ionic equation, because that's going to simplify everything, so we can get rid of half of this stuff. We're not going to involve the sodium ions. We're just going to have the carbonate ions, right? So we're going to have our carbonate ions. Okay, those are going to react with the hydrogen ions out of the acid. The nitrate ions would cancel out. Okay, so we're going to end up with, this is going to react with the hydrogen. I think it's going to be easier to write this as two separate equations, really. So we can say that the carbonate is going to react with the H plus ions, and that's going to make carbon dioxide and water. And then we just balance that like that. And then we can say, and the carbonate ions would also react with the copper ions that were left over, and that's where you get your precipitate from. That's probably the easiest way of doing it. Then we don't need to worry too much about trying to combine that all together. And then I'm just going to cancel out all of this lot just to make it clear that that is not the answer that I want it to be marked. So let's put this here, step 2. So there's actually 2 ionic equations there. Half of it is we were explaining each of the observations. So F of S is, so that's coming from here, and then the precipitate forming is coming from the copper carbonate. So writing it separately is probably the easiest thing to do there. Right, and then we need to do step 4 as well. So step 4, what's going on here? A 25 centimeter cube sample. What happened next? We did this, the precipitate. So the copper, this is now copper carbonate, right? So the copper carbonate is reacted with ethanoic acid to form a solution. Okay. So then a sample of that solution is pipetted into a conical flask, and potassium iodide is added, and we get a precipitate of copper 1 iodide. Oh, okay. So all this is doing then, we're basically just dissolving this precipitate, and we're going to end up then with copper ions in the solution again, and then those copper ions are going to be reacting with the potassium iodide to make these products here. So that's not too bad. Maybe I can squeeze this on the bottom here. So step 4, we're going to have aqueous copper ions again by the time we've reacted our precipitate with the ethanoic acid. It's reacting with, what did it say? It's reacting with potassium iodide. So, but we're doing an ionic equation, so the potassium is going to cancel out. So we're reacting with iodide ions. And then it says it makes a precipitate of copper 1 iodide. So that's just going to be Cui, because that would be copper 1. That'd be Cu plus and I minus. And it said it makes a precipitate, that's a solid. And then it also makes a solution of iodine. Okay. So then we just need to balance this. Well, we've got 3, so that's going to have to be 4 I minuses, make that a 2. That gives me 4 iodines and 4 iodines, and put 2 there. And that balances the charge, doesn't it? Yeah, 4 plus and 4 minus. Okay. Right, that already seems like quite a lot of work. This one question is worth 9 marks, I should say. So we are getting a decent return for doing all this work. I think it's unlikely that you'd get a 9-mark question now on the new spec of exams. But you'd still get asked to do this kind of stuff. They'd just separate it out. I think they'd make this one question, or maybe they might even make these individual questions like worth 1 mark each, and then you'd have a 6-mark question for your calculation for the percentage probably. So although it's an old spec question and you wouldn't get a 9-mark question anymore, you'd probably still be asked to do all the same stuff. They'd just split it up. Okay, so now we need to do the calculation where we want to determine the percentage by mass of copper in the brass. Okay, so now we need to go and look at some of the numbers here. And actually that's the first thing I'm going to do, is just find all the numbers. So I've got a value here. I've got a concentration there. I've got 25 centimeters cubed. I've got 250. And I've got 2.8 grams of brass here. Right, so those are all the numbers that I'm going to have to use. And for me, this just helps so much because there's just so much writing here that trying to find your way through it is a bit of a nightmare. So, right, this is the bit I'm actually looking at. Right, so if we're going to do some calculations, the first thing we want to know is calculate moles. We're going to basically start at the bottom here and work backwards because we want to end up knowing about what's in the brass. That's the final thing it's asking us for. So you kind of work your way back up the page with these questions. So this is where we're going to start. We're going to have our 29.8 centimeters cubed, and we're going to use that and the concentration here to get the moles. Okay. So I'm going to take it's going to be some flicking backwards and forwards, sorry for that. So 29.8 over 1,000, that's going to be decimeters cubed, and we're going to multiply that by the concentration is 0.1. The more you do these titration calculations, the more you will see that they follow the same kind of pattern. Concentration times volume to get moles is pretty much always the first thing that you want to do. Divide that by 1,000, times it by 0.1. Right, we've got 2.98 times 10 to the minus 3 moles of, what is that? And this is really important, guys, that you actually do this. Look at how I'm laying this out. Every time I'm writing something, I'm making sure I put the units so I know what it is. That's a volume, that's a concentration, that's moles. And what have I just calculated? We need to be on top of it here and make sure we know what we're doing kind of at all stages. What we've just done is worked out the moles of the sodium thiosulfate. Okay, so it's the thiosulfate ions really that we're interested in. Okay. And so now what I'm going to do is going to say, right, I've used that number and I've used that number. Okay, and this now we're going to work our way back up the page again. So we've now calculated this, haven't we? Thiosulfate ions. Where are we going to go with this? Well, we're going to have to do the ratio, right? So we're going to do the ratio to get back to the iodine. Okay. Yeah. So it's a 2-to-1 ratio. So we're going to then divide by 2 to get the moles of iodine. Okay. Again, this follows the sort of procedure of working your way up the page. These two things are actually part of the same step, really. We're going to work our way back to this iodine. That iodine came from here, didn't it? That's where the iodine came from. So now we're up to step 4 and we're going to work our way back up from there. So we need to divide by 2. So we're going to say the ratio of iodine 2 thiosulfate is 1 to 2. So 2.98 times 10 to the minus 3 over 2 is 1.49 times 10 to the minus 3 moles of iodine. Okay, right, let's go back here again. So this iodine, what we're going to do with that? Where did this iodine come from? This came from the reaction of the potassium iodide with the copper. All right, so we want to get back to copper eventually, don't we? Because it's the percentage by mass of copper in the brass. So this is what's going to link us back to the copper. The fact that the iodine came from reacting with copper. It was this reaction that we've written down here. So this is what we're going to do next. We know the moles of iodine. So now we're going to do, it's a 1 to 2 ratio to get the moles of copper. So actually we're going to end up back at the same number again. Okay. So we're now going to do the ratio again. And we're going to say the ratio of copper 2 plus to iodine was, just to make sure we get this the right way around, it was 2 coppers to 1 iodine. So it was 2 to 1 that way. So we're going to multiply this by 2 and we're going to get back to that number again. I'm just going to do that on my calculator just so I've got the up-to-date number on the calculator. Right, so that is now the moles of copper. Right, we're getting somewhere now, aren't we? Okay. It was asking us the percentage by mass of copper in the brass, so at least now we've got something about copper. This is good. Right, where are we? We're working our way back up the page. So we now know the number of moles of copper in this solution. This is good. So in work our way back up, we're now going up to a 250 centimetre cubed solution. So from there to there, we're going to have to times by 10, aren't we? Because it's going to be 10 times as many moles in the 250. Okay. So that's what we're going to do next. So that was a number of moles in 25 centimetres cubed. So it's going to be 2.98 times 10 to the minus 2 moles of copper in the 250 centimetres cubed. This is a very common step. It's not always times by 10. Sometimes it's, you know, the original sample was 100 centimetres cubed, you've got to times it by 4. You just read it carefully. Right, so that was the copper. What was going on here? Where did that come from? Came from our precipitate. The brass reacted with that. Right, so all of that, there was nothing else going on here. All of the copper in here has come from the brass. There's not been a sample taken out or anything. So that number of moles of copper in that solution is the number of moles of copper that was in the brass in the first place. Because all that's done here is it's just reacted with, it's just turned from copper into copper 2 plus. So the number of moles is going to stay the same. There's no ratio there, it's a 1-to-1 ratio, right? So that we're looking at, you know, this reaction here. It's a 1-to-1 ratio between copper 2 plus and copper. So, right, if that's the number of moles then, if we want to work out the percentage by mass, we need to do mass, we need to get it into grams. So we're going to need to multiply this by the atomic mass of copper. Okay, so you get your periodic table here. Copper's atomic mass is 63.5. So we're going to times it by that. And that's going to give us the mass. That number I need to times by 10 because I didn't do that on the calculator. So now we've got the right number. Now we're going to times that by 63.5 at 1.8923 grams of copper. Right, and then we want to do this as a percentage by mass of okay, well, good. At least we've got a smaller mass than 2.8 grams. So that's good, right? If we end up doing this and get 4.7 grams, we've got a problem, haven't we? It should definitely be less than 2.8, which it is, so that's good. So we're just going to do this as a percentage of 2.8. Right. We're going to do that number divided by 2.8 times it by 100. And we get... Does it ask us for a certain number of significant figures? Yes, it does. 1 decimal place. Always worth checking that. 1 decimal place. That's a really irritating way to lose a mark. by not doing that. So this wants to be 67.6%, doesn't it? Round it up. All right. Okay, so a fair bit of work there, but actually there's not too much going on in that calculation. Right, it's work out moles, do the ratio, then do the ratio again in another equation. Okay, factor in this factor of 10, and then times it by the atomic mass. And these steps are very similar. They often have this do the ratio twice, and there's very often a 25 centimeters cubed out of 250 or out of 100 or something. So you'll find that the steps are very similar, hopefully.